The directions in this question say, use the second derivative test to find all extrema. Write any relative extrema as an ordered pair. We have the function f of x equals x cubed plus 3x squared. So with the second derivative test, the second derivative test is a test to find relative extrema. And the way that we look for the relative extrema with the second derivative test is that we're going to calculate the derivative. That's 3x squared plus 6x. We're going to find the critical numbers from the first derivative by setting the derivative equal to 0. And that's going to give me 3x times x plus 2. We're going to set each factor equal to 0. And that gives me x equals 0 and x equals -2 as my critical numbers. We don't get any critical numbers from the derivative being undefined since the derivative is a polynomial. So these are the only critical numbers. Then we're going to calculate the second derivative. And the second derivative would be 6x plus 6. And we're going to use the second derivative to figure out if these critical numbers are relative minimums or relative maximums. So we substitute the critical number of x equals 0 into the second derivative, and that's going to give me 6 times 0 plus 6, which is 6. So we've got the second derivative being positive, and the second derivative being positive tells me concave up. Concave up, coupled with the fact that these are critical numbers are when the derivative is equal to 0, and so that means that we have a horizontal tangent line. The slope of the tangent line is 0. So putting those two pieces together, that you have a function that's concave up and a place where the derivative is equal to 0, tells us that we have a minimum value at that critical number. And then we'll do the same thing with the other critical number of x equals -2. We substitute that into the second derivative, and that's going to give me 6 times -2 plus 6, and that's -12 plus 6, and that's -6. So this time our second derivative came out to be negative, which tells me concave down, and that coupled with the fact that this is a critical number tells me that we're going to have a horizontal tangent line. So that point is a maximum. So we found that we have a relative min and a relative max at these critical values. So the first one, the smaller one, would be -2. We want to write that as an ordered pair. The larger one would be at 0. We also want to write that as an ordered pair. And the first one is, we said, was a relative minimum. And the second one is a relative maximum. So to find the ordered pairs, we would substitute -2 into the original function. And that gives me -2 cubed plus 3 times -2 squared. It's -8 plus 12, which is 4. So we've got the ordered pair -2, 4 being a relative minimum. Substitute the other critical number into the original function. That gives me 0 cubed plus 3 times 0 squared equals 0. So the ordered pair 0, 0 is a relative maximum. So the thing I want to distinguish is that even though the name of this test is the second derivative test, it is still just a technique for us to find the relative extrema. We also have the first derivative test, and the first derivative test is looking for relative extrema. So even though we typically use the second derivative to determine concavity and points of inflection, the second derivative test, this process, is used to find relative extrema. On this question, we want to find the derivative using implicit differentiation. We're given the equation y cubed plus y squared minus 5y minus x squared equals -3. Now the reason why the directions say to solve this with implicit differentiation is because this equation is written implicitly. Typically, we would see an equation in explicit format. And explicit format is when you have one variable written in terms of the other variable. For instance, if you have y equals x squared plus 5x plus 4, this equation is written explicitly. Y is written explicitly with x as the variable. So the equation that we're looking at is implicit because we don't have a variable written in terms of another variable. We don't have y equals something with x or x equals something with y. So we're going to use this process of implicit differentiation since our equation is written in that implicit format. So the process for implicit differentiation is that we're going to calculate the derivative with respect to x on each side of the equation. So we have d dx of y cubed plus y squared minus 5y minus x squared. And that's one side of the equation. And then on the other side of the equation, we'll also take the derivative with respect to x. Now, as we take the derivative with respect to x, we can go term by term, and we'll notice in this first term that the variables don't match each other. So when the variables don't match, we have to do an extra process of calculating the derivative with the chain rule. So we're going to take the derivative of y cubed and make that 3y squared. But because the variables don't match, we have to chain by multiplying by the derivative of y. We're going to do the same thing with the next term. That's 2y. Once again, the variables don't match, so we chain and multiply by y prime. The derivative of 5y would be 5, but because the variables don't match, we have to chain and multiply by y prime. We'll calculate the derivative of x squared, and that's 2x. And this time we don't have to chain because the variables do match. We're taking the derivative with respect to x, and the variable is x. On the right-hand side, the derivative of a constant is 0. So once we've calculated the derivative with respect to x on both sides, what we want to do is notice when we have a y prime in our terms. You want to collect all the terms with y prime, the derivative of y, on one side of the equation, and all the terms that don't have y prime on the other side. So we just have one term that doesn't have y prime, so I'll move that one term to the other side of the equation. So I have 3y squared y prime plus 2y y prime minus 5y prime equals 2x. I'm going to factor the y prime out of each of these terms. And that leaves me with 3y squared plus 2y minus 5 equals 2x. And then I can solve for y prime by dividing both sides by what's in the parenthesis. So I'll divide by 3y squared plus 2y minus 5 on both sides. So now I've solved for y prime. That's 2x over 3y squared plus 2y minus 5. And we've now calculated the derivative of y, even though we weren't able to write y explicitly. So now that we've found the derivative of y, we want to find the slope of the tangent line at the point 3, negative 2. So if we remember that the derivative is the slope of the tangent line, we can calculate the slope of the tangent line by substituting our ordered pair into the equation. So for this example, our x is 3 and our y is negative 2. We'll substitute that into the equation for the derivative. That will give me 2 times 3 over 3 times negative 2 squared plus 2y minus 5. That's 6. I forgot to substitute this y in here. So y is negative 2. That's 6 over 3 times 4 minus 4 minus 5. That's 6 over 12 minus 9. 6 over 3 is 2. So we get that the slope of the tangent line is 2. And then we can take it a step further and find the equation of the tangent line. And the equation of the tangent line, we'll use the point slope form, y minus y1 equals m times x minus x1. And I'll substitute the slope that we calculated along with the ordered pair that was given. So this is y minus negative 2 equals 2 times x minus 3. That's y plus 2 equals 2x minus 6. And I'll subtract 2 on both sides. That gives me the equation y equals 2x minus 8 as the equation of the tangent line. So I wanted to provide a graphical representation of what we found. So I've graphed the equation that was given originally, the y cubed plus y squared minus 5y minus x squared equals negative 3. And if you recall, I gave you the point 3, negative 2. And then we were able to calculate the slope of the tangent line to be 2 and the equation of the tangent line to be y equals 2x minus 8. So I've typed in the tangent line so you can see a graphical representation of it here. And you can see near that point 3, negative 2, the graph just touches at that point, giving us this tangent line. Thank you for checking out my videos. Have a great day.